Morning. In the last lecture, we started discussing transport properties of particles, and in particular, we discussed their diffusional characteristics and electrostatic forces that drive particle transport. In this class, we are going to discuss two aspects of particle dynamics that are very crucial in most mechanical operations. The first is drag, and the second is inertia. When a particle is immersed in a fluid, drag is the force that it experiences which opposes its motion. There are two types of drag. There is something called form drag and friction drag. Form drag refers to the resistance to the motion which happens because the particle tries to force molecules out of its way, whereas friction drag refers to a frictional resistance to motion which is associated with its contact with adjacent layers of molecules. So, essentially one is a normal force and the other is a tangential drag force. So, when we talk about drag, there are two expressions that are applicable. One applies in the very low Reynolds number range and the other applies in the higher Reynolds number range. The extremely low Reynolds number case is also called creep flow, where the particle is moving in a fluid at extremely low velocities. So, under those conditions, when Reynolds number is much smaller than 1, the drag force is given by 3 pi mu d dp over cc, where mu is the viscosity, dp is the particle diameter, v is the relative velocity between the particle and the fluid in which it is immersed, and cc is again the Stokes-Cunningham slip correction factor that we had mentioned earlier. As Reynolds number approaches 1 or exceeds 1, then this becomes the aerodynamic drag that you are probably more associated with in terms of fluid mechanics. There is a drag coefficient CD, and that is multiplied by the surface area parameter pi dp squared by 4, and this is multiplied by half rho v squared, where rho is the density of the fluid in which the particle is immersed and v is the relative velocity. The CD value, the drag coefficient itself, is related to the Reynolds number. By the way, you know Reynolds number, right? What is the expression? dp v sorry, it's dv rho by mu, right? If you plot Reynolds number versus CD, plot this in log coordinates. Any idea what the dependence would be? Have you dealt with this in fluid mechanics or somewhere? Basically there is initially there is a linear slope, and then it kind of oscillates, and this represents a dependence of 24 by Re. So, the drag coefficient varies as 24 over Reynolds number in the low Reynolds number regime, and then in the higher Reynolds number regime it kind of stays at a fairly constant value. So, these are the two expressions for the drag that a particle experiences when it is moving through a fluid. In many cases, if you have a fluid in which particles are suspended, there is a gravimetric force that is trying to, a gravitational force that is trying to pull it down. In the case of simple atmospheric gravity, this may be just a g value, or it could even be an accelerated field. You could actually impose a higher gravitational or body force field which can accelerate the force of gravity. And so this introduces a body force Fg or a gravitational force which is opposed by this drag force, right. So, I am sure you have studied this in school. So, what happens as the particle settles, it reaches a terminal velocity, and the terminal velocity is derived as a balance between F drag and Fg you can write as some pi dp cube by 6 times rho p minus rho f times g. This g can be g effective depending on the body force field that is applied. And so, when you do this, of course, rho p is the density of the particle, rho f is the density of the fluid in which the particle is immersed. All you have to do is equate F drag to Fg, and the resulting velocity that you get when you equate those two expressions is called the terminal velocity, right. So, it will be Vt. So, Vt or the terminal velocity is achieved when the drag force and the gravitational force exactly balance each other. You can do this math and you can derive an expression for this V value. By the way, just a quick hint about your quiz. One thing I notice is that you know, in general, in all my classes that I have taught, there is a good correlation between attendance in class and your grade. So, just a quick hint. Anyway, I think you can expect a couple of questions that look at derivation of certain basic principles. For example, you should be able to derive an expression for the terminal velocity from first principles in various cases, in the low Reynolds number case or in the high Reynolds number case. All you have to do is substitute the appropriate drag force expression, and also you should be able to derive the expression for terminal velocity in the case of a simple gravitational field or in the case of an applied centrifugal field. Now, this g value, g effective, can in general be written as the gravitational acceleration plus some sigma squared r, where the sigma value represents your, say, your rotational velocity when you are applying a centrifugal field on top of the gravitational field. So, a general expression for g effective would include both the gravity plus an applied gravity or enhanced gravity due to a centrifugal field that you have applied. So, in general, you should be able to obtain an expression for the terminal velocity in both those cases. The other first principles derivation you should be aware of is something I covered in one of the earlier lectures, which is the Langmuir adsorption isotherm. You should be able to derive an expression for how fractional coverage of the surface in the case of Langmuir adsorption varies with respect to pressure, because that is again it does not require any memorization. It is a first principles application of arrival of molecules and desorption of molecules. Okay, so, when you go through this math, you will come up with an expression where this Vt is a parameter multiplied by g, and this parameter is something that we call tau, which represents the particle relaxation time. You will also find that Vt is proportional to 1 over dp in the regime of larger particles, and it is proportional to 1 over dp squared for smaller particles. Now, it is kind of sorry, it is the other way around. It is 1 over dp squared for larger and 1 over dp for smaller. The implication is actually interesting. You know, when you look at settling of particles, it is clearly a very important mechanical operation. in general, you would expect a particle size dependence. You would expect that heavier particles would settle faster and lighter particles would take longer to settle, right, and that is true. However, you will see that as particle size decreases, the dependence on particle size also decreases. As you go to from micron to submicron, there is a clear increase in the settling time. However, when you go from submicron to nano, the difference in the settling time is much smaller, and once you reach nano dimensions, the settling time is virtually independent of size. Intuitively, it is obvious, if you have nanoparticles that are suspended in a fluid, they are not going to want to settle, they are going to want to float basically. So, the only way that they would settle is through pretty much a random walk process, analogous to diffusion that we talked about earlier. So, in many ways, the settling of a nano-dimensional particle becomes virtually independent of particle size and becomes dependent on many extraneous factors. So, we'll talk about this more when we discuss batch settling and sedimentation later on in the course. But the reason that this is a very important mechanical operation is that it is a very effective way to separate particles by size and mass. So, if you have a column, this could be a sedimentation column, and if you are trying to do analysis, size analysis, or if you are trying to separate the material by size, a convenient way to do this would be to suspend the particles in a liquid, let them settle. They will have varying settling rates based on their size characteristics, and therefore you can separate them. There is another, so this is called batch settling or batch sedimentation. There is a variant of that where you can actually take the fluid out at different levels of this column and thereby effectively again achieve separation of the particles by size, and this process is known as beaker decantation. So, the combination of batch settling and beaker decantation gives you a very effective way of not only analyzing particle size distribution, but also actually separating the particles by size. Okay? And the principle involved is again the balance between drag and gravity. So, it is fairly simple and straightforward. Now, as I mentioned earlier, drag is an important phenomenon in the intermediate particle size range, but as the particle size increases, inertial effects begin to dominate, and particle inertia is again plays a huge role in particle processing in many industries, and inertia is represented by a parameter called Stokes number. Stokes number represents the tendency of a particle to deviate from the streamlines of fluid flow and set up its own trajectory. In other words, it is a measure of the inertia of the particle, its resistance to following the flow of the fluid in which it is suspended, and that turns out to be related to this particle relaxation time parameter. Stokes number is actually the ratio of what is called the particle stopping time to a characteristic surface dimension. So, imagine that you have a particle approaching a surface and it wants to settle. So, you have a surface and you have some fluid flow over the surface. So, these could be the streamlines of flow, and you have a lot of particles that are suspended in this flow. Now, as the particle approaches the surface, you can imagine that the larger particles will not follow the streamlines, but separate from the streamlines and head straight towards the surface. So, you would expect that the capture efficiency or sticking probability of a larger particle is greater compared to that of a smaller particle, because a smaller particle can simply get entrained in the streamlines and never contact the surface. So, this and the other parameter that is of importance is obviously the dimension of the target itself. A parameter that is used that compares the two is the Stokes number. Stokes number represents the ratio of the particle stopping distance S to a characteristic surface dimension, and this S is given by tau times V0 by d, where V0 is the initial velocity of the particles. Tau is again the particle relaxation time, V0 is the initial velocity of the particles. Tau times V0 represents the distance that the particle would travel before it comes to a complete stop. And the larger the size of the particle, the larger will be the distance that it travels. And so, the Stokes number, a higher Stokes number basically means that the particle is larger, and therefore, it has a greater probability of traveling all the way to the surface on which the particle is trying to deposit, and therefore, if you plot capture efficiency versus Stokes number, you will get a behavior that looks like this. The higher the Stokes number, the greater is the probability that it will be captured by the surface on which inertial impaction is taking place. So, what we are basically saying is that if you want to maximize particle collection on an impactor, then you want to maximize the Stokes number. On the other hand, if you want to minimize losses due to inertial impaction and deposition, you should try to minimize the Stokes number, so that you are kind of in this regime rather than in that regime. In fact, when Stokes value exceeds about 0.1, inertial effects start to become very significant. When the Stokes number is less than 0.1, then you can neglect inertial effects for purposes of characterizing the dynamics of the particles. Now, this represents a particle capture behavior only in the inertial regime. So, you could say, for example, that if I want to minimize, I have a process in which I do not want particles to deposit on my surface, right. If I want to minimize deposition by inertial impaction, then you would want to operate at a low Stokes number, which corresponds to a low particle diameter. But then what is the negative consequence of that? There are other transport mechanisms that come into play, right. What we have discussed yesterday, diffusion, electrostatic effects, they actually become stronger when you reduce size. So, you have to be careful. If you are trying to minimize total particle accumulation on a surface, then it is not enough to only consider the reduction due to a particular mechanism. You have to consider the effects of any changes you make on all the processes that are in effect leading to particle transport and deposition. In fact, if you redraw this curve and not look only at inertial impaction, but net, if you take all particle transport mechanisms, then what you will find is something interesting. You will actually see that you have a behavior that kind of looks like this. What is the reason for that? The reason, of course, is that at extremely low Stokes number values, diffusion starts to dominate. See, in a sense, you can substitute dP here for Stokes number because the two correlate pretty well. So, as particle size decreases, even though inertial impaction effects are decreasing, diffusional and electrostatic effects start to increase, and so you will get a higher capture efficiency. The other reason for that, I think I alluded to this in the next lecture also, just like particles can deviate from streamlines because of their inertia, they can also deviate from streamlines because of diffusion. So, a very fine particle, instead of simply following the convective flow of the carrier fluid, could diffuse and deposit on the surface. So, that again enhances the capture efficiency. So, the reason for this type of behavior is that at very low particle sizes, diffusion effects become dominant, and since diffusion leads to deviation of particles from streamlines, it increases the capture efficiency. And similarly, at large particle sizes, inertial effects become important. Inertial effects also lead to departure of particle trajectories from streamlines, and again lead to an increase in capture efficiency. There is a particle size somewhere in the middle, around 0.5 to 1 microns, where the capture efficiency is lowest, because in this size range the diffusional and electrostatic mechanisms have become weak, but at the same time the inertial effects have not completely taken hold. So, the net effect is that there is actually a minimum in capture efficiency at this intermediate size range. So, if you want to look at particle transport, there are multiple mechanisms that come into play. So, let us use the same notation we used last time, which is MP dot, let us call this total. So, this stands for the total mass deposition rate of particles. The dot represents per unit time. If you look at this parameter, this is the sum of MP dot due to diffusion plus MP dot due to convection plus MP dot due to impaction or inertia plus MP dot due to electrostatic effects and so on. These are the, there is also an MP dot due to phoresis, phoretic effects. So, these 5 represent the dominant modes of particle transport, and each one, as we have seen, has a very different particle size dependence, right. In fact, the electrostatic effect can be kind of clubbed into this, because you can look at that as also a phoretic mechanism. Phoresis again is the motion of particles induced by an external field. So, if you look at electric field as an external field, then instead of listing this separately, we can club it into phoretic forces. So, if I look at this expression, how do we write each of these terms? I think we have done this earlier. So, you can write the diffusional deposition as rho times dP times gradient in omega p, right. That is the Brownian diffusional rate that we looked at earlier. And by the way, this is a flux term. So, you have to multiply it by the area, the projected area of the surface in order to get a rate. So, you would take this and multiply this by a projected. So, the projected area is the area that is actually exposed to the flow of the particulate laden fluid. Typically, the projected area is roughly half of the total surface area in most cases, approximately. It is very rare that the entire surface is exposed to the flow. So, as a reasonable estimate, you can say that the projected area is roughly 1/2 of the total area of the object. So, this is a diffusional component. How do you write the convective component? In convective transport of particles, the particles are just going along with the flow. So, the particle flux is set by the flux of the carrier fluid. There is no deviation of the particle from the streamlines of flow. So, you can simply take rho times u, which is the convective flux of the carrier fluid, because this is kilograms per meter cube times meter per second. So, it has units of kilograms per meter squared second, which is a flux term, and you can multiply this by omega p, which is the mass fraction of particles in the fluid, and again to get a rate you multiply this by the projected area. Let us look at the phoretic force next, or phoretic deposition. In general, you can write that as a rho times omega p times Cp, where this parameter rho times omega p represents the total mass of particles in the fluid times Cp, which is the velocity that is associated with this phoretic field, and again this will be multiplied by A projected. So, what do we mean by phoretic velocity? Let us say that you have a pipe in which flow is happening and there are particles suspended, and you have a temperature gradient. So, the top wall is at some temperature Th and the bottom is at some temperature Tc. So, this sets up a temperature gradient, right. When there is a temperature gradient applied across a force field, it actually induces a velocity in the particles that are suspended there, and that is called the thermophoretic velocity. Which would be then written as Cpt. So, it stands for the phoretic velocity associated with a temperature gradient. In general, particles that are heavier than the carrier fluid will tend to move from the hot zone to the cold zone. So, the particle motion will be in the direction of Th to Tc. This thermophoretic velocity is also known as Soré velocity or Soré diffusion. That is just another name for the velocity that is associated with thermophoresis. So, the Cp, in the case where temperature gradient is driving transport, will be Cpt, which can be derived by looking at the temperature gradient as well as the molecular properties of the particle, such as again its size characteristics and so on. In the case where this field is electric, if there is an electric gradient, a charge gradient, then the corresponding velocity will be some Cpe, it will be known as electrophoretic velocity. So, it is a phoretic velocity that is induced by a gradient in the electric field that is applied on top of this flow field. And of course, there can be a magnetic gradient. If you have magnetic particles that are flowing in a suspension and you apply magnetic field across the flow, you get a magnetic phoretic velocity. You can even have gravity can actually be looked at as a phoretic velocity also. So, again, instead of considering this as a separate field, you can club this into the phoretic field, and so Cpg will be simply the velocity typically the terminal velocity that is associated with a balance that you achieve between a gravitational field and a drag field that the particles are exposed to. There is even something called a diffusiophoresis field. It is an interesting phenomenon that when particles diffuse, they set up a concentration gradient, and as soon as a concentration gradient is set up, in order for mass balance to be preserved, it induces an opposing flow of particle mass, and that is called diffusiophoresis. It is phoresis that is induced by diffusion, and that has a characteristic velocity Cpd associated with it. So, the point is Cp in this expression is a general term that refers to all induced velocities due to an applied force field, but it can take different values depending on whether the applied force field is thermal in nature or electrical or magnetic or gravitational or diffusional and so on. And then of course, there is the impaction mass flux, which depends on the Stokes number, as we have seen. How do you represent that? Clearly the mass deposition or mass transport due to impaction has to involve the so called capture efficiency. So, this term mp dot impaction is obtained by looking at two parameters. If you have a surface with a fluid that is flowing on top of it or normal to it, there is going to be a net rate of particles arriving on the surface, but not all of them are going to stick to the surface, right. So, the arrival rate, particle arrival rate is given by rho times u times omega p times A projected, where rho u represents a mass flux of the carrier fluid. When you multiply that by the mass fraction of particles, that gives you the mass flow of particles, and then when you multiply it by the projected area of the surface, this tells you how many particles are actually flowing past the surface per unit time. You then have to, if you want to look at particle deposition rate, which is the rate at which particles are actually accumulating on the surface, then you have to take this and multiply it by the capture efficiency parameter, and that is where the previous graph that we drew so this is a function essentially of Stokes number. That is why Stokes number is a very important parameter in determining the rate at which particles deposit inertially on a surface. Okay. So, this expression then, I mean mp dot impaction, you can substitute rho u omega p A projected multiplied by eta capture. So, that kind of summarizes all the different mechanisms that lead to particle transport and the associated fluxes and the associated rates of transport. So, the point I was trying to make earlier is, if you are trying to minimize this particle transport flux, then you cannot just minimize one of these mechanisms. You have to, if you are trying to tweak something in your process to minimize, you have to look at its effect on each of these terms and make sure that the end result is something that you like. Okay. And again, it can be based on product sensitivities. If you know for sure that your product is only sensitive to small particles, then you try to minimize inertial impaction, because that gets rid of large particles. On the other hand, if you are sure that your product is only sensitive to fine particles, then you try to maximize inertial impaction and minimize diffusional and electrostatic mechanisms. The problem is most products, most processes are susceptible to a fairly wide range of particle sizes. So, it is somewhat simplistic to think that you can determine which is your most sensitive size and just cut particles off at that size range. There is going to be some overlap. You are going to have to design a process which is a good compromise between what you need to achieve and what it is going to take to achieve it. Anytime you try to work on one of these processes and affect its magnitude, there is cost associated with it, there is processing time associated with it, and all of these process engineers do not like. So, there is always this trade off between trying to improve the quality of your process or product versus the cost of improving the quality. And depending on the industry you are in, you could make a decision one way or the other. There are certain industries, particularly large volume consumer products, where the main determinant is price. Then you would err on the side of minimizing cost, even if it means that your quality is not as good as it should be. On the other hand, if you are selling a product in the high end where quality is the differentiator, then you would probably feel that it is worth making the additional investment to achieve a delta improvement in quality, because that will enable you to distinguish yourself from your competitors, maybe enable you to get market share, profit margin, and so on. So, it is a delicate decision that you need to make. So, when we look at all these various transport processes associated with particles, there are certain dimensionless numbers that become important. I am sure as chemical engineers you are all familiar with the dictum that if you want to understand a process, you have to derive the most relevant dimensionless parameters and use those intelligently, because whatever results you get have to be scalable. So, if you get results on a small system, you have to be able to scale the results to a larger system. Scale up, which is something that chemical engineers are supposed to be very good at, only becomes possible if you can identify and derive the most relevant dimensionless numbers for every system that you are dealing with. So, in the next lecture we will talk about a few dimensionless parameters that are of particular importance to particle transport, and look at how they can be related to basic fluid parameters such as Reynolds number and Prandtl number and Schmidt number and so on. The other aspect we will talk about is that mass transport is very difficult to measure experimentally, because we are talking about micrograms of materials, and it is hard to measure in a repeatable and reproducible manner. So, is there a possibility that you can make, for example, temperature measurements, and from that extract information about particle transport characteristics? That is an interesting exercise, and we will talk about that some more in the next lecture. Any questions on what we have covered today? Okay, so I will see you next Monday then.